Hello everyone, my name is Xiaofei from Alibaba Group. Today, I will introduce the GANAS Aero, a cloud-native system for big raster data management and processing. Before introduce the GANAS Aero, I want to brief some challenges of current Rust-based application. For geoinformatics applications, such as online map or Earth observation, the original Rust data is always cut into small tails with the same width and height to accelerate the computation or visualization. However, there are several disadvantages for this tiny method. First, it needs extra storage space to save the generated tails from the original Rust dataset, which causes data redundancy. Second, if the original Rust dataset is updated, we have to regenerate the changed tails in order to get the latest information. And this tiny process is always time-consuming. At last, the separation of computation and visualization is not efficient for the interactive analysis, which is of extreme importance for scientific analysis. Okay, to overcome these challenges, we developed the GANAS Aero. The GANAS Aero is designed to manage and process big Rust data by leveraging the cloud-native database technologies provided by PolarDB GANOS. The GANOS is a special database engine that is built on PolarDB, and PolarDB is a cloud-native relational database system developed by the Alibaba Cloud. It provides high elasticity and concurrency, and it is built on and fully compatible with the PostgreSQL. One of the most important features of GANAS Aero is that it makes full use of the cloud-native abilities provided by the Alibaba Cloud, which make it possible to push many time-consuming operations down to database for execution, including on-the-fly computations or batch processing jobs. And the user can do some interactive analysis in Jupyter by interacting with the backend database, which will be shown at the latest demonstration. Okay, this figure shows the abstract Rust model used in GANAS Aero. As shown here, the multi-source Rust data can be represented by Rust object, which can be divided into a series of bands. Each band can be seen as a two-dimensional array. The band can be further divided into tails, and the pyramid model can be built from these tails. All of the tails can be stored in a low-cost and infinite capacity cloud storage system called Object Storage Service, or OSS for short, of Alibaba Cloud, which is another important feature of GANAS Aero. Based on the Rust model introduced above, this feature shows how GANAS Aero organizes Rust data in database. Firstly, we designed a native data type called raster, which can be used to store the Rust objects. The Rust table and pyramid table can be stored in OSS as mentioned above. Secondly, a custom Spark reader was developed to load Rust data into Spark as the data frame object, which make it possible to leverage the rich features of Spark to fulfill various tasks. So here, let me summarize our contributions. First, the GANAS Aero is cloud-native and provides features such as high-performance data accessing, resource auto-scaling, and fault tolerance. Secondly, the GANAS Aero supports efficient data management and big data processing on the same copy of the Rust data thus reducing the storage cost and avoiding the expensive data transferring and transformation. At last, by adding the RAS data as the native data type and pushing operations to be conducted in the DBMS, the Ganus Arrow achieves efficient on-the-fly tail production for both the interactive query and batch task processing. Now let me introduce the usage of Ganus Arrow. First, we need to load the CQL extension Jupyter to query the table called Landsat 8 demo in our database. You can see that there is a column with a raster data type. Then we can add this raster object to map panel for displaying as a new raster layer by sending the query statement to the server-side database for execution directly. Here you can see that the image has been added to the map. Please note that all of the tails were generated dynamically, which avoids extra storage space for storing these tails. Now let's insert another 2 images into this table. And you can find that this layer was updated automatically without the need to produce new tails. Ganus Arrow is designed to process large volumes of raster data. Here we use another raster table called Landsat 8, which contains about 9,000 Landsat 8 raster images covering the globe. You can see that this table has the same schema as the previous raster table. We can add this table to the map panel as a new layer for displaying and move, zoom in or zoom out the layer. I want to emphasize again that all of the tails were generated dynamically from the original raster data in the Ganus Arrow without need to pre-generate tails for displaying. Now let us do a more complex operation called NDVI, which has been widely used to reflect the health condition of vegetation. Here we use a UDF called ST normalized difference to compute the NDVI from the band 1 and band 3. This function will be sent to database for execution, and the returned result is shown on the map synchronously. All of the result was computed and rendered dynamically as well. We can also apply Ganus Arrow to do more complex analysis. For example, we can compute the NDVI of each state of USA and classify the result into different levels and count pixel numbers of each level. Firstly, we create a table called states, which contains the boundary of each state in the form of a geometry object. And we can query the boundary of a state and display it on top of the NDVI layer as shown on the map. Secondly, we have developed a custom Spark data driver to load the raster data into Spark as a data frame object. You can see that a CQL statement was sent to Spark as a parameter of job, which contains a UDF called stReclassify. This UDF can be used to classify the pixel values into different categories, which is 1, 2, 3, 4 in this demo. At last, we can apply the Spark to do the statistical analysis. And the returned result is shown in a new table panel, as shown here. You can see that the NDVI of each state is classified into 4 categories, which represents different levels of vegetation density or health condition. That's all of the demonstration. Thank you.